And if we flip back to our cheat sheet here, we can see, again, after the equivalence point, we're going to use an ICF table to determine the number of moles that are in excess. And here again, where this problem becomes different from what we did in our first lecture. In order to find the concentration of that hydroxide, we need to take the moles of hydroxide that's in excess and divide by the new volume that we have, because we've been mixing things together. That will give us the new amount of hydroxide, and from there we can get POH and then pH. So hopefully that made sense to walk through sort of the qualitative piece. So let's take a moment then and work through the actual calculations. Now, I've already worked through the calculations that we have here, but again, I'm going to encourage you, I will pause or give you an opportunity to pause the video if you'd like to work through the calculations on your own, or again, you can just let the video play to see how the calculations are worked out. So let's imagine, again, the first part here, and I didn't actually pause this here. Hopefully this is sort of a review for you guys. If we've got 40 milliliters of a 0.1 molar HCl solution, before we've done anything with any titration, if we just think about what's there, we've got HCl in solution. Being a strong acid, it completely dissociates. Chloride's a spectator, not anything to worry about. We haven't added anything else, so there's no chemistry to consider. Because we haven't added anything else, there's no volume changes to consider. So with strong acid stuff, there's not going to be any equilibria that we need to consider. So the pH is really a reflection of the acid concentration, because that completely dissociates to give us a full amount of hydronium ion. So again, we know that the acid concentration is 0.1 molar, so that means the hydronium ion concentration is 0.1 molar. So again, the pH is the negative log of that H3O plus concentration. Negative log of 0.1 tells us that the pH before we start is going to be equal to 1. So that's more of kind of a chapter 18 type problem. What's the pH of a 0.1 molar HCl solution? It's going to be 1. And keep in mind, I hope it makes sense, it doesn't matter if we had 40 milliliters or 400 milliliters. The fact is that concentration of H3O plus will be the same. Okay, so now let's imagine that we've added 20 milliliters of sodium hydroxide to the 40 milliliters of HCl that's in our beaker. So again, we're going to use an ICF table to figure out, and it's just again a way to keep track of what's going on, to figure out what's left. So see if this makes sense here. We've got 40 milliliters of 0.1 molar HCl that's in solution. Again, chloride is not going to be affecting anything here. So 40 milliliters of 0.1 molar HCl that's in our beaker. And we're going to be adding 20 milliliters of 0.1 molar hydroxide. So we've added 0.002 moles of hydroxide, and we had 0.004 moles of H+. So put those into an ICF table like we have here. The relevant chemistry in a strong acid, strong base titration is H+ plus OH- gives water. So again, hydroxide here is going to be our limiting reagent because we are before the equivalence point. So again, we have 0.002 moles of hydroxide, 0.004 moles of H+. We know that OH- is going to be our limiting reagent. It's the smaller number there. We're going to use up all of it, and that also dictates how much H+ we use up. So at the end here, we're going to have a final number of moles of H+ we have of 0.002, and we've reacted all of the hydroxide. Okay, so here's where this problem becomes different. We see that we've changed the volume because we've mixed things together. We had 40 milliliters in our beaker, and we've added 20 milliliters. So I'm going to give you guys a chance to pause the video and see if you could work out the rest of the solution. We need to figure out what's the concentration of H+, because if we know the concentration of H+, we can figure out pH. So see if you can figure that out, and then start the video again to see if your answer is correct. So finishing out this problem, we started with 40 milliliters in our beaker. We've added 20 milliliters from our burette. So the new volume is 60 milliliters. So this is the number of moles of H+. We don't want to take negative log of that. We need to figure out what's the concentration of H+. So to figure out the concentration of H+, we are going to take the number of moles of H+, which we have right there, and divide by the volume of the solution, which we have right here. So the new molarity of H+ is 0.033 molar. Okay, we've actually decreased some of it. Remember, we started out that it was 0.1 molar, so now it's down to about a third of what we started with. Okay, now again, take the negative log of that number. That will give you the pH. So take a minute, pause if you need, take a look at this to make sure you understand why we're not taking negative log of that. Remember, this is the number of moles. We need to take the negative log of a concentration, not a negative log of a number of moles. And how this problem becomes different from what we did in our first lecture is we considered the fact that when we added that hydroxide, it came in a solution. So we need to consider how that volume change is affecting things. So not only are we decreasing the amount of H+ that we have, we're actually diluting it because we're changing the volume. Okay, so the next one is going to be thinking about at the equivalence point. I'm going to show you here with this calculation, but I'll let you know if you know you are at the equivalence point of a strong acid, strong base titration, you can just say answer is going to be 7. But I'm going to show you real quickly here with our calculations why that's the case. So when we're at the equivalence point, we know we've got 0.0044 moles of H+, and we've added 0.004 moles of OH-. That's bigger than we had in our previous calculation. So looking at what we have here, neither of these is really the limiting reagent. This is what it means when we have stoichiometric equivalence. I know that sounds like a really big word, but when we're doing a limiting reactant problem, that really just means nothing's left over. Nobody's a limiting reactant. We've got the perfect matched amount of each. So again, what this means is we're going to have no hydronium ions that are left because we added the exact perfect amount of hydroxide. So at the end of the day, there's really nothing left to contribute to pH. Those guys are equal. And so we're going to have a pH that's equal to 7. So again, none left here at the equivalence point. That's going to mean that the pH will be equal to 7. So again, this is what we call stoichiometric equivalence, and that's when we have the number of moles of acid that are reacted equals the number of base that are added from our burette. Again, you don't need to do anything with the calculation. If you know that you have a strong acid, strong base titration, the pH at the equivalence point is going to be equal to 7. All right, last point here. We are going to be at the point where we've gone beyond our equivalence point. Now the only thing that's going to be affecting the pH of the solution is the excess hydroxide that we've been adding. So let's take a look at that here. Again, always kind of have this part in the beginning where we say who's in solution. Well, we didn't add any more stuff to our beaker. We still only had 40 milliliters of 0.1 molar HCl, so we still only had 0.004 moles of H+. But now in adding a total of 60 milliliters of sodium hydroxide, that means we've added 0.006 moles of our hydroxide. Now what this really means is our H+ has become our limiting reagent. So we have an excess now of our hydroxide. So I encourage you, pause the video here. We know the number of moles of hydroxide that are in excess, but how do we figure out the concentration of hydroxide that is in excess? And then how do we use that to figure out pH? So go ahead and pause the video if you want to try to figure this out on your own, or just let it play to see the worked out solution. So we treat this problem the same way we treated it when we were before the equivalence point and we had an excess of H+. We need to account for the fact that the volume has changed. So we started out with 40 milliliters in our beaker. We've added 60 milliliters from our burette. So the new volume that everything is together in is 100 milliliters. So that 0.002 moles of OH minus that's in excess is now contained in 100 milliliters. So taking the ratio of these two will give us the concentration of hydroxide that's in excess, which is 0.02 molar. Taking the negative log of this gives us POH, but remember, to get pH, we can just subtract that from 14, and we get pH equal to 12.3. This should be a red flag for you if you wanted to write down that the pH was 1.7, because we know we should have an excess of hydroxide here. We should have a pH that's greater than 7. Okay, so hopefully that wasn't too much to kind of hurt your brain, but to kind of highlight how we handled the calculations for each of these points. Before the titration begins, because we've got a strong acid, whatever the initial acid concentration is, just take the negative log of that, and that's your pH. Pretty straightforward there. That's a chapter 18 kind of problem, but pretty straightforward because we've got a strong acid. Before the equivalence point, what that means is when we add our titrant, it's not going to be in excess. We're still going to have some of the strong acid that's in our beaker being in excess. We can use an ICF table to figure out exactly how many moles are in excess, because the hydroxide that's added from our burette in this case is going to be the limiting reagent. So we'll determine the moles of H plus that are left over. And then we need to make sure to divide by the total volume, because the volume has been changing because we've been dripping our titrant in order to figure out the H3O plus concentration, we need to know the moles that have remained and then divide by the new volume that we have. Again, point 3, you actually don't even need to do a calculation. If you know that you've got a strong acid, strong base titration, by definition, the pH will be equal to 7. No calculations need to be done. We actually just did the calculations there to highlight and prove that we didn't have any excess acid or base at that point. After the equivalence point, the flip happens of what happened at before the equivalence point. After the equivalence point, now we're going to have hydroxide in excess. It was H plus that was still in excess in the previous step. So now, having hydroxide in excess, we can now divide by the total volume, and we're going to be able to figure out then hydroxide concentration. Remember, that will give us POH. We need to subtract that from 14 in order to give us pH.